Every action you take, from walking down the street to dropping your phone, is bound by strict parameters: time, distance, and force. Before mechanical clocks, early civilizations had to rely on natural phenomena to track the day. Curious, they used the shifting alignment of shadows cast by the sun to carve up the daylight hours. By harnessing periodic motion, specifically the reliable back-and-forth swing of a pendulum, we figured out how to measure time mechanically. Today, we rely on quartz crystals. When placed in an electric circuit, these microscopic crystals vibrate with extreme, predictable accuracy, giving us the precise time down to the millisecond. Whether we are measuring shadows on a stone or electrical pulses in a microchip, the objective remains exactly the same: standardizing that basic universal unit of measurement we call the second. Moving across distances has evolved significantly over human history. We started on foot, eventually harnessed animal power to pull carts, and ultimately built engines capable of launching spacecraft. To measure any of that movement mathematically, you first need a reference point. You cannot define an object's location or its speed without a fixed starting marker, an origin. Motion is entirely relative. A train passenger is completely stationary compared to the person sitting next to them, but they are moving very quickly relative to someone standing outside on the platform. Without establishing that strict, fixed reference point, your time and distance data means nothing. You simply cannot calculate true motion. Once we know an object is moving, we measure its speed by dividing the total distance it traveled by the time it took. If we add a specific direction to that speed, we get velocity. This velocity time graph reveals a new calculation. The shaded rectangular area bounded by the specific time interval and the constant velocity represents the total distance the object has covered. When velocity changes, we get acceleration. We track this using 3 specific equations. We use variables for initial velocity, final velocity, acceleration, and distance. Engineers use these exact mathematical frameworks to predict the precise future position of any accelerating object in the real world. This diagram shows an object moving along a multi-sided track. Running around a hexagon or octagon forces you to change direction at every corner. Increase those sides to infinity, the corners become infinitesimally small, and the shape morphs into a perfect circle. Because the direction on a circular path is continuously changing, the velocity is continuously changing too. This means the object is constantly accelerating, even if it is moving at a perfectly steady speed. Objects naturally resist any change to their state of motion. We call this physical resistance inertia, and we measure it quantitatively by an object's mass. This brings us to Newton's second law, which calculates the exact physical push needed to alter an object's speed. If the applied force is 0, an object sitting at rest will perpetually remain at rest. This schematic illustrates Newton's third law inside a firearm. When one object exerts a force, the second exerts an equal force in the opposite direction. The explosion pushes the bullet forward, creating an equal backward recoil force. This diagram shows the exact same principle on a human scale. If you leap forward off a small, untethered boat, your forward push generates an equal reaction that shoots the boat backward into the water. Forces never act in isolation. Every piece of motion you observe is dictated by these continuous, mathematical push and pull interactions between different masses. This push and pull applies to gravity too. The Universal Law of Gravitation dictates that a force exists between all objects. However, if you double the distance between 2 objects, the gravitational pull drops to 1/4 of its original strength. Calculating this specific equation for our planet yields a strict universal baseline constant for Earth's gravitational pull. Galileo famously proved this constant. By dropping objects from high balconies, he demonstrated that in the absence of air resistance, objects of entirely different masses will fall at the exact same rate. Earth's gravity provides an absolute, inescapable baseline acceleration. We can plug that constant directly into our motion equations to predict exactly how and when any object will hit the ground. We can manipulate these physical laws to our advantage. Pressure is simply the distribution of a heavy weight over a specific surface area. Biological evolution already uses this physics rule. A camel's wide feet spread its massive body weight across a larger area, reducing the pressure so it doesn't sink into soft desert sand. Modern engineering mimics this biology exactly. Heavy military vehicles use wide, continuous metal tracks to massively distribute their weight and reduce ground pressure. Engineers also have to contend with friction, the physical resistance between two sliding surfaces. By inventing the wheel, humanity shifted from sliding friction to rolling friction, a mechanism which is drastically less restrictive. By mathematically manipulating surface area and friction, we have engineered clever ways to bypass physical limitations. Mastering the raw formulas of motion gives us the absolute toolset to conquer the physical world around us. If you are sitting in a pitch-black room, your eyes are useless. Human vision only occurs when light strikes a physical object, ricochets off its surface, and enters your pupil. We divide the objects around us into two categories. Luminous objects, like the sun or a light bulb, generate and emit their own light. Opaque objects, which make up almost everything else we see, simply reflect it. If an opaque object blocks a light source entirely, it leaves behind a shadow. This diagram illustrates the first law of reflection, which dictates exactly how that light bounces. When an incoming ray strikes a smooth surface, we can draw a perpendicular line right at the point of impact, called the normal. The angle the incoming ray makes with that line exactly matches the angle of the light bouncing away. The second law of reflection adds another strict rule. The incoming ray, the bouncing ray, and that perpendicular normal line don't scatter randomly into 3D space. They are all locked together on a single flat plane. Light does not bounce in chaos. Because it follows these precise mathematical angles, our brains can trace those light rays backward to decode the exact size, shape, and location of the physical world around us. A flat mirror gives you an exact, life-sized reflection, but if you curve that reflecting surface, you change how the light behaves. A spherical mirror curving inward is called concave, while one bulging outward is convex. A concave mirror forces incoming light rays to converge. It pinches them together to meet at a single focal point. Dentists use small concave mirrors to magnify the image of a tooth, and solar engineers use massive ones to concentrate sunlight into intense, usable heat. Convex mirrors do the exact opposite. Because they bulge outward, they force light rays to diverge or spread apart. This shrinks the reflection of individual objects, but pulls in light from a much wider area, which is why your car's rearview mirror is convex. This diagram shows the new Cartesian sign convention, the mathematical framework we use to calculate these reflections. By treating the exact center of the mirror, its pole, as the origin point on a graph, we can precisely measure the object's distance on the negative left side against the focal length to predict exactly where the image will form. By understanding how a specific inward or outward curve alters the focal length, we engineered mirrors to shrink, magnify, and bend reflections to fit our specific needs. Light travels at 300 million meters per second in a vacuum, but entering a new transparent medium, like water or glass, it abruptly slows down. That sudden change in speed causes the light ray to physically bend and change direction, a process called refraction. We measure a material's ability to slow light down using the refractive index. Air has an index very close to 1, meaning light barely slows at all. But dense materials like glass drag that speed down significantly, causing a much sharper angle of refraction. Spherical lenses exploit this bending property. A convex lens is thicker in the middle, using refraction to converge light rays to a sharp focal point. A concave lens is thicker at the edges, forcing the light rays to bend outward and diverge. Opticians don't guess how much a lens will bend light. They calculate its exact converging or diverging power using a unit of measurement called diopters. The shorter the focal length of the lens, the higher its diopter power, and the sharper the angle of refraction. Combining different lenses with precise diopter ratings allows us to build complex optical systems. The same mathematics of refraction power, a jeweler's magnifying glass, and the deep space lenses of an astronomical telescope. White light is actually a tightly packed bundle of different colors. When white light enters a triangular glass prism, the different colored wavelengths bend at slightly different angles. Red bends the least, and violet bends the most. This splits the beam into a distinct band of colors, a phenomenon known as dispersion. Look at the scale of the light spectrum in this photograph. A rainbow happens when millions of suspended water droplets act as miniature prisms. Sunlight enters the raindrop, refracts, reflects off the back of the droplet, and disperses into the distinct bands of colors spanning the landscape. The atmosphere acts as a massive optical medium. Starlight entering Earth's atmosphere passes through layers of hot and cold air with shifting densities. This continuously refracts the light ray back and forth, making the star's position appear to flutter or twinkle from our perspective on the ground. The atmosphere is also packed with microscopic dust and water particles. Through a process called the Tyndall effect, these tiny particles intercept sunlight and aggressively scatter the shorter blue wavelengths of light in every direction, while letting the longer red wavelengths pass through. Because of that aggressive scattering, the sky overhead appears blue. Without our atmosphere refracting and dispersing the sunlight, the daytime sky would simply be a dark, empty void. This diagram details the human eye's anatomy, which operates like a camera. Light enters the cornea, passes through the crystalline lens, and projects an inverted image onto the retina. To focus, ciliary muscles contract to stretch the lens, modifying its focal length. When the eyeball is elongated, light rays converge too early, forming an image in front of the retina. This causes myopia. We fix this by placing a diverging concave lens in front of the eye to spread the light out before it enters. Hypermetropia, or farsightedness, occurs when the eyeball is too short, causing the focal point to land entirely behind the retina. By placing a converging convex lens in front of the eye, we pull that focal point forward so it strikes the retina cleanly. Eyeglasses and contact lenses are external physics patches. We calculate the exact diopter needed to correct the mechanical failure of the biological lens, forcing the light rays back onto the correct visual plane. But humans only represent one way to process light. In this photograph, a butterfly's eyes are constructed from thousands of individual facets, allowing them to capture light from the front, sides, and back simultaneously. When the biological mechanics of the human eye fail entirely, optical correction isn't an option. The individual has to bypass light completely and interpret physical reality through non-optical sensory pathways. Notice the dense, raised dot patterns in this photograph of an open book. Developed by Louis Braille, this system translates visual language into 63 physical dot combinations, allowing visually impaired individuals to absorb complex information entirely through touch. This photograph shows the renowned author and lecturer Helen Keller in her university graduation regalia. After losing her sight, she utilized tactile tools like Braille to access academic material, eventually earning a college degree and publishing multiple books. The physical laws of reflection and refraction rigidly control how light moves through the universe, but when the biological tools to capture that light break down, human ingenuity steps in, building entirely new sensory pathways to ensure that everyone can continue to perceive and understand the world around them. We live inside a massive, invisible machine. Every time you flip a switch, check your phone, or open a refrigerator, you are tapping into a continuous stream of electrical energy. Modern infrastructure depends on this flow. The ability to route power across entire continents is what allows our hospitals, factories, and cities to keep running long after the sun goes down. But beyond the switches and power lines, what is actually moving through the walls of your house? To understand electricity, we have to look at the physical reality of the flow. If we zoom in on a typical copper wire, we find a material with very low resistance. Copper is a conductor, meaning it easily allows electric charges to pass through. Rubber or plastic, which we use to coat the wires, are insulators. They offer high resistance and block that flow. Scientists once thought electricity flowed as positive charges. Actually, negative electrons move in the opposite direction. Despite the circuit's speed, individual electrons crawl. Inside a copper wire, they drift roughly 1 millimeter per second. So why does a light bulb turn on instantly? Because the moment you close the circuit, an electric field shoots through the wire near the speed of light, pushing every single slow-moving electron forward at the exact same time. This equation defines flow mathematically. Current, I, is charge moving past a point over time, measured in coulombs. 1 coulomb is roughly 6 quintillion electrons. When 1 coulomb passes every second, you have 1 ampere of current. But those electrons won't move on their own. They need electric pressure. We call this potential difference, or voltage. It is the work done by a battery to push that charge through the circuit. In 1827, a German physicist named George Simon Ohm discovered a strict mathematical relationship here. He proved that the voltage across a metallic wire is directly proportional to the current flowing through it, provided the temperature stays the same. This brings us to resistance, the property that slows electrons down. It depends on three factors: the material itself, the length of the wire, and its cross-sectional thickness. A longer, thinner wire creates more resistance. Voltage is the push, resistance is the bottleneck, current is the resulting flow. This is Ohm's law in action. Look at this schematic. This is a series circuit. All components are joined end-to-end in a single path. Because the current has to force its way through every single resistor in line, the total resistance is simply the sum of all individual resistances. But a single path creates a critical vulnerability. If one component fails, the entire loop is broken. The current stops completely, and every device on the circuit shuts down. Now compare that to this parallel circuit diagram. Here, the components are arranged across multiple branches. The math flips. The reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances. Because the current has multiple paths, adding more branches actually lowers the total resistance. The current simply divides among the active branches. If one bulb burns out, the other components are completely unaffected. This mathematical reality is why your home is wired in parallel. It allows a toaster, a reading lamp, and a television to draw different amounts of current and operate entirely independently of one another. This graphic shows us electric power, which is the actual rate at which energy is consumed. Power equals voltage multiplied by current. By substituting Ohm's law, we can also calculate it as the current squared multiplied by resistance. The standard unit of power is the watt, but 1 watt is a tiny amount of energy. To track power on an industrial scale, we use kilowatts. If you operate a 1,000-watt device for exactly 1 hour, you consume 1 kilowatt-hour of electrical energy. This is the commercial unit you see on an electricity bill. The physical push and flow of electrons is directly quantified into the energy costs we pay every month. When an electric current passes through specific liquids, it creates a chemical effect. In industry, this is used for electroplating. The current separates metallic ions from a solution and deposits them onto a target object, which is exactly how modern car parts are coated in anti-rust zinc, or cheap metals are plated in real gold. We can also see this equation at work, Joule's law of heating. When electrons collide with the atoms of a resistor, that kinetic energy turns into heat. The heat produced is directly proportional to the resistance, the time the current flows, and crucially, the square of the current. We harness this heating effect for safety. A traditional electrical fuse uses a wire made of a specific alloy. If a short circuit causes the current to spike dangerously high, the immense heat generated instantly melts the wire, breaking the circuit before a fire can start. Today, buildings mostly use miniature circuit breakers, or MCBs. Instead of a melting wire that needs replacing, these use mechanical switches that automatically trip off during an overload. Managing resistance allows us to dictate how energy is released, transforming raw electrical flow into predictable chemical reactions and thermal safety systems. The final major consequence of flowing charge is the magnetic effect. Any active current-carrying wire naturally generates a magnetic field. If you coil that wire around a piece of iron, the field concentrates, creating an electromagnet. This diagram of a classic electric bell shows exactly how useful that is. When the switch is closed, current flows into the coil. It becomes a magnet, forcefully pulling the iron strip to strike the gong. But it's a deliberate loop. Moving forward breaks the circuit at the contact screw. The magnet turns off, the spring resets the strip, current resumes, and it strikes again. This simple mechanical loop clearly proves that electromagnetism allows us to turn invisible voltage into controlled, repeated physical motion. Look at the relationships on this dashboard. Current is charge over time. Voltage is the work required. Resistance throttles that current, and Joule's law dictates the heat. Whether that current is flowing through a single vulnerable path in a series circuit or dividing efficiently across a parallel grid, the math remains absolute. These mathematical laws represent our absolute control over the electron. Because we can calculate the flow, we can transform invisible current into the precise light, heat, and motion that define our civilization. Imagine walking across a rocky hillside thousands of years ago, and suddenly your walking stick is physically pulled to the ground. According to ancient Greek legend, this happened to a shepherd named Magnus. The iron tip of his staff snapped right onto a strange rock. This was a documented physical reality. He had stumbled upon a naturally occurring iron-rich mineral. We now call this dark, textured stone magnetite. Today, we manufacture artificial magnets on a massive scale to manipulate heavy materials. Look at this industrial crane. By running electricity through the large disk, it generates enough magnetic force to effortlessly lift and sort tons of jagged scrap iron. Recognizing this mysterious rock was the first step in identifying a new natural law. By observing how these stones behaved, we began to see how an invisible pull could be used as a practical tool for sorting metal. If you take a magnet and test it against random items, you'll quickly notice a strict rule. Magnets ignore almost everything. They only interact with specific magnetic materials, namely iron, nickel, and cobalt. You can actually pull this hidden iron straight out of the earth. If you drag a regular magnet through loose sand or soil, you will extract tiny, dark specks. Those are iron filings naturally dispersed in the ground. Look closely at this diagram to see how those filings stick. They cannot coat the surface of the magnet evenly. Instead, they flock immediately to the two extreme ends, leaving the middle section almost completely bare. This demonstrates that a magnet's pulling force is highly concentrated at specific points. We call these active ends the poles. Locating these poles is critical. All of that concentrated power at the ends dictates exactly how the magnet will move, push, and pull against the world around it. Recognizing these physical poles led to early navigational mechanics. According to historical records, Emperor Huangti of China navigated unfamiliar territory using a chariot equipped with a freely rotating statue that always pointed south. That trick relies on a planetary interaction. If you suspend a bar magnet from a string so it can spin without friction, it consistently locks into a predictable north-south line. Earth itself acts as a giant magnet, pulling on the smaller one. By isolating a magnetized needle inside a protective dial, we harnessed this natural alignment to create the compass. Sailors suddenly had an accurate directional guide, even under thick cloud cover. You can replicate this orientation mechanically. If you take an ordinary iron needle and stroke it repeatedly in one direction with a permanent magnet, the needle absorbs that magnetic property. Float it on a piece of cork in a bowl of water, and it will immediately snap straight to the Earth's north-south axis. By deciphering how a sliver of magnetized iron reacts to the planet, early explorers built the reliable navigation system necessary to map the globe. Bring two magnets together, and they follow strict interaction rules. Line up the north pole of one magnet with the south pole of another, and they attract. They pull toward each other and snap together. But if you flip one around so two identical poles face each other, north to north or south to south, they repel. An invisible cushion of force pushes them apart, resisting your pressure. Despite this pushing and pulling power, a magnet's internal alignment is physically fragile. If you heat a permanent magnet over a flame, strike it hard with a hammer, or drop it onto the floor, you can shatter its internal structure and erase its magnetic properties. To prevent this degradation, they require careful storage. You must pair them with opposite poles facing each other, place a wood separator between them, and keep them far away from consumer electronics. While magnetic force provides incredible mechanical utility, it exists in a delicate physical state that requires specific operational care to maintain. Up until the 19th century, magnetism was treated as an isolated property of specific metals. But in 1820, a scientist named Hans Christian Ørsted noticed a mechanical link between two entirely different areas of physics. Ørsted built a basic electrical circuit using a copper wire, positioned right above a compass. The moment he completed the circuit and let the electrical current flow, the compass needle below it swung violently out of its north-south position. The electricity traveling through the wire was physically moving the magnet. He discovered that a flowing electric current creates a magnetic field. We map the shape of this invisible pulling force using paths we call field lines. These field lines follow strict geometric rules. Outside the magnet, they always flow from the North Pole to the South Pole. They loop back inside to form closed circuits. Their proximity indicates the strength of the pole, and critically, they never intersect. Ørsted proved that magnetism is a dynamic force generated by the movement of electricity. This discovery provided the foundational physics for the motors, telecommunications, and electrical grids that define the modern world. Look at this dashboard summarizing the physical properties we've covered. It started with magnetite, a natural stone that attracts specific metals like iron, nickel, and cobalt. That force is localized entirely at the poles, where opposite poles pull together and identicals push apart. Moving to the dynamic properties mapped out here, we took the Earth's natural alignment to build reliable global navigation. Then, Ørsted's circuit proved that electricity generates its own magnetic field, governed by perfectly parallel closed-loop field lines. The timeline from Magnus to Ørsted tracks our progress from observing a curiosity to mastering a fundamental force. This understanding transformed an ancient mystery into the measurable science that runs our universe. Welcome to Arvindra's classes. Today, we are tracing the life cycle of a disturbance to understand the physics of sound. Try to imagine a completely silent world. No cars honking, no birds singing, no voices. What exactly are those everyday sounds made of? At its core, sound is a specific form of mechanical energy. It occurs exclusively when a physical object vibrates. To see this in action, we can look at our own biology. The human voice box, or larynx, sits right at the upper end of the windpipe. When your lungs force air upward through a narrow slit, those stretched vocal cords rapidly vibrate. Human communication is forced biological vibration, turning the breath from your lungs into mechanical energy. But that energy operates under strict physical rules. It cannot travel in a vacuum. Sound absolutely requires a physical medium to move through, like a solid, a liquid, or a gas. Think of the particles in that medium like commuters on a crowded train. A push on one side ripples through the group, transferring the wave's energy while the individual particles oscillate around their original positions. This creates alternating pressure zones in the air. The crowded, high-pressure areas are compressions, marked C. The spread-apart, low-pressure areas are rarefactions, marked R. Because particles oscillate parallel to the wave's direction, physicists call this a longitudinal wave. Sound traveling across a room is an invisible domino effect of oscillating air pressure. This graph shows how we map those physical compressions and rarefactions into a standard sine wave, visualizing the invisible data points of the disturbance. The number of oscillations that happen per second is the frequency, measured in hertz. A tightly packed wave has a high frequency, which your brain interprets as a high pitch. Then there's the height of the wave from its resting point, called amplitude. Measured in decibels, amplitude determines loudness. A taller wave carries more energy and produces a louder sound. The physical distance between two consecutive compressions is the wave's wavelength, represented by the Greek letter lambda. The speed of sound is the product of wavelength and frequency, and it varies based on the environment. Sound travels significantly faster through solids and at higher temperatures. Every sound in the universe, from a quiet whisper to a roaring jet engine, is entirely governed by these three mathematical properties. Traveling waves bounce off solid surfaces like a rubber ball hitting a wall. Under the right conditions, this creates an echo. Your brain needs specific parameters to hear it distinctly. The reflected sound has to return after a minimum gap of 0.1 seconds. In open air, that requires standing at least 17.2 meters away from a massive, hard surface. If you trap those reflections inside an enclosed space, you get a continuous persistence of sound called reverberation. Doctors harness this exact property in every stethoscope, channeling multiple internal reflections of a heartbeat up to the ears. Our ears have biological limits, detecting only those frequencies falling between 20 Hz and 20,000 Hz. Frequencies pushed above that 20 kHz ceiling are called ultrasound. We use these extreme, invisible frequencies to detect microscopic flaws in industrial metals and for advanced medical imaging. This diagram shows a boat utilizing sonar. A transmitter sends ultrasound waves down to the seabed, and a detector catches the reflection. Knowing the speed of sound in water, we calculate depth using a simple formula. Total distance equals velocity times time. Mastering the reflection of extreme frequencies allows us to see deep underwater and inside the human body using only sound. Sound also carries environmental risks. Urban expansion and heavy machinery generate immense amounts of unwanted, excessive sound, known as noise pollution. Prolonged exposure to noise above 80 decibels triggers severe medical consequences, including anxiety, high blood pressure, and permanent hearing impairment. Mitigating this requires active architectural and civic planning, enforcing industrial zoning away from residential areas, installing engine silencers, and planting dense rows of trees to act as natural sound absorbers. Unchecked wave amplitude is a systemic biological hazard that requires architectural mitigation. To understand why high amplitude is dangerous, we look at the human receiver. Sound waves are caught by the funnel-like outer ear and channeled down the auditory canal. Here, waves strike the eardrum, a stretched membrane converting air pressure directly into biological vibration. These vibrations pass through the tiny bones of the inner ear, where they are transformed into electrical signals. The auditory nerve then fires those signals directly to the brain. Let's lock in the core mechanics. Sound is a longitudinal wave. High frequency creates a high pitch. High amplitude creates high volume. Distinct echoes require a 17-meter gap, and above 20,000 hertz is ultrasound. Thank you for joining this session at Arvindra's classes. Keep questioning the physics of the world around you. Look around you. The objects we interact with every day, a block of ice, a wooden desk, appear completely solid. They seem seamlessly continuous, as if they are made of one unbroken block of material. We can test that continuity with a simple glass of water. If you drop a spoonful of salt in and stir, it seems to vanish. If water were truly an unbroken, seamless liquid, there would be no physical room for the salt to inhabit. This diagram illustrates the reality. Matter is particulate. Everything is constructed from unimaginably tiny spheres, separated by vast empty space. The salt didn't disappear. Its particles simply slip into the invisible voids between the water particles. What our eyes perceive as a smooth, solid world is effectively an illusion. The physical behavior of the salt and water demonstrates that the macroscopic world is built on a foundation of separate particulate matter. Every particle in the universe is locked in an invisible tug-of-war. On one side, kinetic energy, the energy of motion, pulls particles apart. On the other side, intermolecular attraction acts like a magnet, trying to pull those particles tightly together. This three-part illustration shows what happens when attraction wins. In a solid, particles lock into a rigid, vibrating arrangement. Add heat, and they break those bonds, flowing freely as a liquid. Apply extreme heat, and they fly completely free, expanding to fill their container. Because gas particles are so widely dispersed, they leave massive amounts of empty space between them. This illustration shows how we exploit that space. By applying pressure, large volumes of gas can be forced tightly together into much smaller spaces. By shifting the temperature or applying physical pressure, we change the balance of that tug-of-war. We are manually forcing particles to lock together or fly apart, reshaping the material state. This graph plots temperature against heat energy added to a substance. Notice that as a solid melts or a liquid boils, the line strictly flattens out. The temperature stops rising. This is latent heat, energy working entirely to break the physical bonds holding particles together. While boiling involves raising the temperature of the entire bulk liquid, evaporation is a surface phenomenon. A fraction of the surface particles gather enough kinetic energy to break free and escape as a vapor. As they leave, they steal heat energy from their surroundings, leaving the remaining surface cooler. Under certain conditions, matter completely bypasses the liquid phase. This schematic shows a sublimation apparatus. When solid camphor is heated, it transitions directly into a gas, without ever melting into a liquid first. These phase changes track the precise breaking and reforming of microscopic bonds. Every plateau on that temperature graph represents energy being funneled into physical restructuring. In the natural world, scientifically pure substances are incredibly rare. Almost every material we encounter is a complex mixture of multiple different elements and compounds. These mixtures fall into different categories based on how their particles behave. In homogeneous solutions like salt water, the solute particles are perfectly blended throughout. In heterogeneous suspensions like muddy water, particles clump together and settle to the bottom. This diagram compares a flashlight beam hitting a true solution versus a colloid. Colloids sit right in the middle. Their particles are suspended evenly, but they are physically large enough to intercept and scatter a beam of light. That scattering phenomenon is known as the Tyndall effect. You can see it clearly in this photograph. Sunlight filters down through the dense forest canopy, and tiny water droplets suspended in the air act as a massive colloid, making the atmosphere visible.
Milk, fog, and soda might all look like uniform substances, but the hidden scale of their internal particles dictates entirely different physical behaviors when they interact with light, gravity, or heat. By understanding exactly how these invisible particles combine and interact, we gain the ability to physically pull them apart on a macroscopic scale. We can exploit the physical differences in particle size to isolate what we need. This illustration shows the process of sieving. By passing a mixture through a mesh, smaller particles fall through the perforations, leaving the larger impurities trapped behind. We can also exploit variations in mass and density. This photograph captures the process of winnowing. By dropping a harvested mixture from a height, ambient wind carries away lighter husks, leaving heavier grain seeds. This schematic demonstrates decantation, which relies on density. When heavier solid components settle at the bottom of a liquid, a process called sedimentation, we can carefully pour off the clear, lighter liquid from the top without disturbing the sediment. From industrial-scale harvests to water purification and chemical refining, every process of extraction relies on these specific physical separations. We cannot see the individual particles that make up the universe, but by mapping their rules, their attractions, their kinetic motion, and their physical geometry, we can actively architect the materials that build our modern world. Everything you see, touch, and measure, from a galaxy down to a single drop of ocean water, is constructed from the exact same building materials. To understand the mechanics of the macroscopic universe, we have to look past the surface and examine its absolute smallest components. Welcome to Arvindra's classes. Today, we are going to trace the complete timeline of atoms and molecules. This is a historical progression that stretches from early philosophical thought experiments in ancient India all the way to the precise mathematics of modern quantum chemistry. Tracking how each successive generation of scientists dismantled previous models provides the conceptual foundation required for competitive exams and an accurate understanding of modern chemistry. The concept of a fundamental building block begins around 500 BC in India. The ancient philosopher Maharishi Kanad posed a simple thought experiment. If you take a piece of matter and continuously divide it, what happens? Kanad reasoned that you would eventually reach a stage where further division is physically impossible. He named this absolute smallest particle Parmanu. Around that exact same time, Greek philosophers Democritus and Leucippus reached an identical conclusion. Democritus called these particles atoms, meaning indivisible. For over 2 millennia, this remained a purely philosophical idea. By the late 18th century, the focus shifted to empirical proof of how elements actually combined. Lavoisier's law of conservation of mass states mass is neither created nor destroyed in a reaction. Total weight remains identical. Additionally, Proust's law of constant proportions proves every 9 grams of water always yields exactly 1 gram of hydrogen and 8 grams of oxygen. That 1:8 ratio remains absolute regardless of where the water is sourced or how the compound is prepared. These mathematical laws proved that matter interacts in highly predictable ways. Now, scientists had to determine what the physical building blocks actually looked like to make such precise proportions possible. In 1808, British chemist John Dalton stepped forward to explain these chemical laws with his own atomic theory. Dalton stated that all matter is composed of tiny spheres that are indivisible and indestructible, but his primary postulate would soon collapse under new evidence. By the end of the 19th century, studies of static electricity and gas discharges revealed that atoms were not solid units, but contained smaller, charged components. In 1900, J.J. Thomson identified the first of these, a negatively charged subatomic particle we now call the electron. E. Goldstein had already observed positively charged canal rays, providing the first evidence of the proton, a particle with a charge equal to the electron but opposite in sign. The trio of particles was finalized in 1932 when J. Chadwick discovered the neutron, a particle massive as a proton but entirely lacking in electrical charge. Dalton's indestructible spheres were gone. The atom was now recognized as a complex container of positive, negative, and neutral subatomic charges. The discovery of these diverse charges immediately forced a new question. How are they actually oriented inside that tiny volume? J.J. Thomson proposed the Christmas pudding model. He theorized that the atom was a sphere of positive charge, with negative electrons embedded throughout it like dry fruits in a pudding. Ernest Rutherford sought to test Thomson's arrangement physically using a new experiment. Rutherford fired fast-moving alpha particles at a gold foil just 1,000 atoms thick. Being heavier than protons, he expected them to pass through with slight deflections. Most did pass straight through, but 1 out of every 12,000 particles rebounded, ricocheting 180 degrees. Rutherford concluded that because most particles passed cleanly through, the atom is mostly empty space. The positive charge and mass must be concentrated in a tiny central volume called the nucleus. This physical evidence dismantled Thomson's pudding model, revealing a structure where electrons orbit a dense central core at a vast distance. Rutherford's nuclear model faced a major objection: orbital stability. Any particle in a circular orbit undergoes acceleration and radiates energy. A revolving electron would lose energy and fall into the nucleus, causing a collapse. If Rutherford's model were entirely correct, matter would be highly unstable. Yet the physical world around us is clearly stable. Niels Bohr resolved this by proposing a series of specific postulates to save the atom. This diagram shows Bohr's discrete orbits. Electrons are restricted to specific shells, labeled K, L, M, and N. While locked in these orbits, the electrons do not radiate energy. To govern how these shells are populated, Bohr introduced the formula 2n², where n is the orbit number. The first shell holds only 2 electrons, while the second holds 8. Crucially, outer shells will not fill until inner shells are saturated. Bohr's work proved that the stability of the universe relies on these strict, unbreakable mathematical limits on electron distribution. Bohr's atomic structure explains why substances react. Every chemical interaction is dictated by the occupancy of the outermost shell. Elements with 8 electrons in their outer shell are chemically inert. Other atoms react by sharing, losing, or gaining electrons to achieve this stable octet. The specific number of electrons in atom exchanges or shares to reach that octet is known as its valency, its fundamental combining capacity. Shifting focus to the nucleus, we define an element by its atomic number, or Z, which is simply the number of protons it possesses. The mass number, denoted as A, is the total sum of protons and neutrons, or nucleons, in that nucleus. Atoms of the same element with the same atomic number but different mass numbers are isotopes. Atoms with different atomic numbers but the same mass number are isobars. These nuclear variations have vital real-world roles. Uranium isotopes fuel reactors, cobalt isotopes are used in cancer treatment, and iodine isotopes treat goiter. While an atom's valency drives its chemical interactions, its nucleus provides the key to advanced medical and industrial technologies. Atoms rarely exist independently. They aggregate in large numbers to form the molecules and compounds that make up visible matter. To manage this diversity, the IUPAC standardizes element names and symbols across all languages. While many symbols match their English name, others use Latin roots. Iron is Fe from ferrum, sodium is Na from natrium, and potassium is K from kalium. When metals and non-metals combine, they form charged species called ions. Positive ions are cations, and negative ions are anions. Chemical formulas are written by balancing these charges. By crossing the valencies, such as magnesium's 2+ and chlorine's 1-, we arrive at the balanced formula for magnesium chloride, MgCl2.
These standardized symbols and formulas allow chemists globally to predict interactions with mathematical precision. There remains one practical problem. Atoms are too small to weigh individually in a lab. How do you measure out a reaction for an experiment? The atomic mass unit, based on 1/12 of a carbon-12 atom, is useful for theory, but impractical for large-scale measurement. To bridge the microscopic and the macroscopic, scientists use the mole. 1 mole represents exactly 6.022140076 times 10 to the 23rd power particles of any given substance. This is the Avogadro constant. It's defined as the number of atoms in exactly 12 grams of carbon-12. This creates the central rule of chemical measurement. The mass of 1 mole equals its relative atomic or molecular mass in grams. We have traced the journey from ancient philosophical guesses through Dalton's spheres and Thomson's pudding to Rutherford's nucleus and Bohr's shells. Moving from the concept of parmanu to the exact mathematics of the mole represents humanity's ultimate success in decoding the universe.
We identify acids by their sharp, sour taste. This property is built into the name itself, derived from the Latin acere, meaning sour. These substances are part of our daily biology and diet. Acetic acid gives vinegar its bite, while lactic acid creates the distinct tang in curd. Bases represent the opposite chemical nature. Compounds like baking soda are characterized by a bitter taste and a slick, soapy texture when touched. These properties extend far beyond our kitchens. The atmosphere of Venus is dominated by thick, yellowish clouds of sulfuric acid, creating a corrosive environment on a planetary scale. Taste and texture serve as our immediate physical evidence of the deeper chemical properties that govern the materials around us. Because tasting unknown chemicals is hazardous, we use indicators to safely detect acidity or alkalinity. Common natural examples include litmus and even turmeric. These materials change color to signal a chemical state. Litmus turns red in acid and blue in a base, while a yellow turmeric stain will flash red when exposed to basic soap. To move beyond simple color changes, we use the pH scale to measure chemical strength mathematically. This 0 to 14 range identifies 7 as neutral, with lower numbers indicating increasing acidity and higher numbers indicating increasing alkalinity. This scale allows us to plot common substances with precision. Gastric juice sits at a highly acidic 1.2, pure water marks the neutral 7, and milk of magnesia reaches a basic 10. By quantifying these properties, the pH scale turns subjective sensory experiences into objective scientific data. When an acid and a base are mixed, they undergo neutralization, a process where both solutions cancel each other out to produce salt, water, and heat. This reaction is vital for human comfort. Indigestion often occurs when the stomach produces excess hydrochloric acid, leading to pain and irritation. To resolve this, we introduce a base. Antacids like milk of magnesia contain magnesium hydroxide, which reacts with and neutralizes the excess stomach acid. From managing our internal biology to treating acidic soil for agriculture, our well-being relies on maintaining this fundamental acid-base balance. We distinguish between physical changes, where no new substances are formed, and chemical changes, where atoms are rearranged into entirely new compounds. Every chemical change is dictated by the law of conservation of mass. In a closed system, matter is neither created nor destroyed. This principle requires every chemical equation to be balanced. As this scale shows, the total number of atoms present in the reactants must equal the total number of atoms found in the products. This conservation ensures that every reaction, no matter how complex, can be mapped with mathematical precision. Most chemical changes fall into 5 specific categories. Combination reactions merge multiple substances into one, while decomposition reactions break a single compound into simpler parts. In displacement reactions, a highly reactive element forces a weaker one out of its compound. Double displacement involves an exchange of ions between 2 different reactants. Finally, redox reactions involve the movement of oxygen and hydrogen. Oxidation is defined by the gain of oxygen, while reduction is the loss of oxygen. We see oxidation's effects in the rusting of iron. When metal is exposed to moisture and air, it reacts to form iron oxide, resulting in a brittle reddish-brown coating. However, historical engineering reveals ways to resist this decay. The ancient iron pillar of Delhi has stood for 1,600 years without rusting, a testament to early advances in metal technology. Whether it is the preservation of ancient monuments or the digestion of food, all visible chemical changes are driven by these 5 microscopic interactions. To understand the behavior of acids and bases, we must look at their reaction with metals. This process generates a salt and releases hydrogen gas. This reaction occurs because all acids share a core mechanism. They dissociate in water to produce hydrogen ions. This release gives acids their reactive properties. Bases operate through a similar but distinct mechanism. Instead of hydrogen, they generate hydroxide ions when they dissolve in water. These invisible ionic exchanges are the microscopic engines that produce the macro-level acid and base behaviors we observe. Common sodium chloride, table salt, is a foundational raw manufacturing material used to synthesize much of our modern world. Through the chlor-alkali process, we use electricity to decompose a saltwater brine into 3 essential industrial products. The process separates these components by charge. Chlorine gas is collected at the anode, while hydrogen gas and sodium hydroxide solution form at the cathode. These outputs are then used to manufacture secondary compounds, including bleaching powder for sanitization, baking soda for food production, and washing soda for industry. Mastering a simple neutralization product like salt enables the industrial-scale manufacture of compounds used to clean our water, leaven our food, and sanitize our hospitals. In summary, chemical behavior is defined by ions. Acids produce hydrogen, bases produce hydroxide, and their intensity is measured on the 0 to 14 pH scale. All these reactions must follow the law of conservation of mass, meaning every chemical equation we write must be perfectly balanced. Thank you for exploring these chemical mechanics. Subscribe to Arvindra's Plus for more deep research into the subjects that matter most for your exams. Command of these foundational chemical interactions provides the technical grounding to navigate both natural systems and modern industrial technology. Welcome to Arvindra's classes. Today, we are breaking down the exact properties used to categorize every piece of matter you interact with. Mastering these concepts provides a framework for understanding how the physical world operates. We start by filtering materials through 5 specific criteria: their state of matter, their appearance or luster, their solubility in water, their behavior as a metal or nonmetal, and their degree of transparency. This diagram shows a beaker of water testing buoyancy. The leaf floats, while the key and coins sink due to density. Their tightly packed particles create a downward physical force that overpowers the water's upward push. Whether an object floats or plummets is dictated by how tightly its microscopic atoms are packed together. Let's focus on metals. In their standard solid state, metals are hard. You can hit them to produce a ringing sound, beat them into flat sheets because they are malleable, and pull them into thin wires because they are ductile. Nonmetals generally behave the opposite way. They are brittle and block electrical currents. But look at this raw graphite sample. Graphite is a non-metal form of carbon, yet it is an excellent conductor of electricity. And here we see liquid mercury poured into a petri dish. It is a highly dense metal, but remains entirely fluid at room temperature. Identifying these exact exceptions, like conductive nonmetals or liquid metals, separates a deep grasp of material science from simple memorization. Beyond physical traits, metals react intensely with their environment. Burn a metal in air, and it bonds with oxygen to form a basic metal oxide. Aluminum and zinc behave differently. They form amphoteric oxides, which are compounds that react with both acids and bases. This diagram shows metals reacting to water. A heated iron sample exposed to steam on the left triggers a chemical process. Following the delivery tube to the inverted test tube on the right, hydrogen gas bubbles up, proving the reaction occurred. We map these interactions using the reactivity series. This table ranks elements from highly reactive potassium and sodium at the top, down to stable gold at the bottom. A highly reactive metal will always displace the less reactive metal from its compound. Commit this descending order to memory. The reactivity series functions as a strict predictive hierarchy, telling us exactly which elements will dominate others in a chemical displacement. We pull these metals from the Earth as ores, mixed with useless impurities known as gangue. This flowchart maps the two options for extracting mid-reactivity metals using heat. Roasting heats the ore in the presence of air, while calcination heats carbonate ores without air. The highly reactive metals at the top of the series cannot be extracted with simple heat. They require electrolytic refining, using electric currents to separate the pure metal from the compound. These three test tubes show the environmental threat of corrosion. Tube A proves that iron requires both moisture and atmospheric oxygen simultaneously to form hydrated iron oxide, or rust. Remove the air or moisture, as seen in the other tubes, and the iron remains intact. This macro texture shows copper corrosion. Exposed to carbon dioxide and moisture, the surface forms a green mixture of copper carbonate and copper hydroxide. Modern human infrastructure relies entirely on fighting the reactivity series. We spend energy to extract pure metals and apply protective layers like galvanization to stop them from oxidizing back into the Earth. Now we shift to carbon. Carbon has a valency of 4, meaning it must share electrons to stabilize. This forces it to form strong covalent bonds with up to 4 other atoms, a property called tetravalency. It can also form long chains by bonding with itself, a process known as catenation. These 3D rotating models show how the exact same carbon atoms build completely different physical forms, or allotropes. On one side, we have the rigid, interlocking tetrahedral network of a diamond. On the other, the stacked sliding hexagonal sheets of graphite. Carbon also forms homologous series, long sequences of hydrogen and carbon atoms. By swapping out a single hydrogen atom for a specific functional group, like an OH hydroxyl group, we rewrite the molecule's chemical identity, turning a standard hydrocarbon into an alcohol. Because carbon can infinitely self-link and modify its molecular structure, it serves as the necessary chemical foundation for all organic life. We leverage these carbon structures daily. This 3D model shows a single soap molecule approaching an oil droplet on fabric. The molecule has 2 opposing ends, an ionic head that actively seeks water, and a long hydrocarbon tail that actively seeks oil. When you wash a shirt, the hydrophobic tails pierce the grease to escape the water. The molecules cluster together into a spherical formation called a micelle, lifting the oil droplet entirely off the fabric so it can be rinsed away. Let's lock in what we've covered. Density controls buoyancy. Aluminum and zinc form amphoteric oxides. The reactivity series dictates chemical displacement. Ores are heated via roasting in air or calcination without air. Iron only rusts when exposed to oxygen and water simultaneously, and carbon's catenation builds the organic world. The Technocrat dashboard here summarizes the exact vocabulary you need for your exams. Pause the video, study the terms, and you will be ready.
Consider this experiment. Place one hand in cold water, the other in hot. Then move both into a lukewarm bowl. One hand feels cold, the other hot. Human touch is a relative sensor, easily deceived by temperature differences. Objective measurement requires calibrated thermometers. A clinical thermometer handles the narrow range of the human body. Laboratory thermometers are designed to measure a much wider spectrum, typically from -10 to 110 degrees Celsius. This specific instrument comes with a rigid usage constraint. It must be read while completely immersed. Because the mercury reacts immediately to the surrounding air, the reading begins to shift the moment the bulb is removed from the substance. Managing these thermal forces effectively requires using these objective, calibrated instruments rather than relying on subjective human senses. Heat moves through the environment via 3 primary mechanisms: conduction through solids, convection through fluids and air, and radiation through a vacuum or medium. Convection drives a coastal cycle. By day, hot air rises over the faster heating land, pulling in a cool sea breeze. At night, the loop reverses. The ocean cools slower, so warm sea air rises, drawing a cool land breeze out from the shore. Radiation, however, requires no physical medium at all. This is exactly how solar heat reaches our planet, and it dictates our clothing strategies, like using light-colored reflective fabrics to bounce heat radiation away in the summer.
By identifying these heat transfer mechanics, we can accurately predict weather patterns and design infrastructure for extreme climates. While sunlight is an inexhaustible energy source, the fuels that power modern transit and industry are finite. These exhaustible resources take millions of years to form and cannot be replaced once consumed. 300 million years ago, the Earth was covered in dense forests and low-lying wetlands. Natural processes buried these forests under layers of soil, where they were slowly compressed by the weight of the Earth. Under intense pressure and high internal temperatures, this vegetation underwent carbonization, a chemical process that slowly converted dead plant matter into solid coal. This raw coal is processed into essential industrial derivatives like coke for steel manufacturing. It also yields coal gas for heating and coal tar for synthetic dyes and plastics. Today's industrial output relies on the aggressive extraction of this thermal energy, vaulted by nature over geological timescales. Petroleum has a similar biological origin, formed from ancient marine organisms. Over millions of years, heat and pressure transformed these remains into oil and gas, which settled into layers above groundwater due to their lighter density. Commercial extraction began in 1859 with the world's first oil well in Pennsylvania. By 1867, India discovered its first deposits in the river basins of Assam. Refining this raw, foul-smelling crude is a complex fractional process. It takes place in towers like these, separating the oil into distinct constituents, including petrol, diesel, and bitumen for road surfacing. Natural gas is often found trapped above these petroleum deposits. It is stored under high pressure as CNG and serves as a cleaner, less polluting alternative that can be delivered directly through pipeline networks. A nation's economic power is often tied directly to its ability to extract and refine these specific subterranean carbon layers. Releasing the energy stored within these fuels requires combustion. It is a chemical reaction requiring three specific inputs: a fuel source, a steady supply of oxygen, and reaching the material's specific ignition temperature. When this reaction occurs rapidly, it results in an explosion. This is a violent release of heat, light, and sound, exemplified by the timed ignition of fireworks. Analyzing the structure of a flame reveals its chemical zones. The bright, luminous center indicates the presence of unburnt carbon particles glowing in the heat. The outer, non-luminous zone is the absolute hottest part of the flame. Goldsmiths utilize this specific area, using blowpipes to direct this concentrated heat for melting precious metals. Technological advancement is driven by the precise manipulation of these ignition thresholds and focused oxygen supplies. Emergency fire control relies on the laws of physics. Water extinguishes fire by cooling the fuel below its ignition point, while the resulting steam displaces the surrounding oxygen. Water is dangerous for electrical or oil fires because it conducts electricity and sinks below fuel. In these cases, dense carbon dioxide gas is used to blanket the fire and displace oxygen without damaging sensitive equipment. Let's review the critical data. Laboratory thermometers range from -10 to 110 Celsius. Convection drives the coastal breeze cycle. Carbonization takes 300 million years, and the hottest part of a flame is its outer invisible zone. Managing global infrastructure requires a strict adherence to these fundamental principles of physics and chemistry. Mastering this topic requires a command of the core vocabulary, the clinical kink that holds a temperature reading, the carbonization of ancient forests, the refined petrochemicals of industry, and the ignition temperature that triggers the release of energy. Understanding and conserving these limited resources is essential for building a sustainable industrial future. If you want to construct a massive stone monument, you don't start with the roof. You start by laying down a single solid brick, and then you repeat the process. Biological life operates on the exact same logic. Back in 1665, an English scientist named Robert Hooke looked at a slice of cork through a rather primitive piece of hardware. He noticed it was made of tiny, hollow compartments and called them cells, Latin for little rooms. Decades of subsequent research by scientists like Leeuwenhoek, Brown, and Purkinje slowly revealed that these weren't empty rooms at all, but rather complex environments filled with a fluid called protoplasm. This sequence of observations culminated in the mid-19th century with the cell theory. Formulated by Schleiden, Schwann, and Virchow, it established two undeniable rules. All plants and animals are composed of cells, and every new cell arises directly from a pre-existing one. By isolating this microscopic unit, biologists finally had a starting point. To decipher the complex architecture of any living organism, you first have to understand the mechanics of a single cell. Every living cell requires a few basic structural components to operate. First is the plasma membrane. It acts as a selective outer boundary, permitting necessary nutrients to enter while blocking harmful materials from getting inside. Plant cells take this a step further. Because plants are stationary and exposed to the elements, they feature an additional rigid outer covering called a cell wall. Composed of complex cellulose, this wall provides the structural strength needed to withstand extreme environmental changes without bursting. Deep inside that boundary is the nucleus. This is the central control vault. It houses the cell's chromosomes, which hold the DNA, the strict biological blueprints dictating inheritance and cellular organization. This diagram shows a side-by-side comparison of the two major categories of cellular life. On the left, we have smaller prokaryotic cells, measuring 1 to 10 micrometers. They lack a distinct membrane around their genetic material, leaving an undefined region called a nucleoid. On the right, we have larger eukaryotic cells, ranging from 5 to 100 micrometers, characterized by a well-defined encapsulated nucleus. That physical encapsulation of the DNA matters. By compartmentalizing their internal structure, eukaryotic cells can safely manage more complex genetic instructions, allowing organisms to grow beyond a single microscopic unit. This technical diagram details the cross-section of an animal cell. The internal volume is filled with a fluid called cytoplasm. Floating within this fluid are distinct membrane-bound structures called organelles. They operate like highly specialized municipal departments within a self-contained city. Right outside the nucleus, we find the endoplasmic reticulum, acting as the manufacturing sector. The rough ER, studded with ribosomes, synthesizes proteins. Right next to it, the smooth ER manufactures lipids and works to detoxify poisons. Once manufactured, materials are sent to the Golgi apparatus, those flattened parallel sacs, to be modified and packaged. Meanwhile, waste is handled by lysosomes. Filled with digestive enzymes, they clear out damaged cell parts, earning the nickname suicide bags. None of this functions without power. Mitochondria act as the cell's generators, producing energy in the form of ATP molecules. In plant cells, this energy production is augmented by specialized plastids, like chloroplasts, which drive photosynthesis. By isolating competing chemical reactions into dedicated membrane-bound zones, a single cell achieves maximum operational efficiency, surviving and thriving entirely on its own. But a single efficient cell isn't enough to build a complex organism. To repair physical injuries or simply grow, cells have to replicate. They do this through a highly regimented mechanical process called cell division. Looking at this flowchart, we can track the first mechanism, mitosis. This is the standard procedure for general tissue growth. A single mother cell duplicates its DNA and splits cleanly into two daughter cells. Both new cells inherit the exact same chromosome count as the original. As the chart updates, we see a distinct reproductive pathway known as meiosis. Instead of a single split, the cell undergoes two consecutive divisions. This produces 4 entirely new cells, each containing exactly half the number of chromosomes of the mother cell, ready for biological reproduction. These precise copying protocols ensure that an organism can multiply from a solitary unit into billions of specialized cells without corrupting the original genetic blueprint. When millions of these cells cluster together to perform a localized function, they form a tissue. Because plants are anchored to the ground, their tissue architecture prioritizes heavy-duty structural support, relying heavily on thick, dead cells. This diagram illustrates a plant root tip, marking the specific locations of meristematic tissues. Plants only grow in these specific targeted regions, the apical, lateral, and intercalary zones, where highly active cells rapidly divide to push the plant upward and outward. Once these cells mature and stop dividing, they differentiate into permanent tissues. Simple permanent tissues like parenchyma handle food storage, while the tough, dead cells of sclerenchyma provide stiff outer armor, like the husk of a coconut. Inside, complex vascular tissues take over logistics.
Xylem pulls water and minerals up from the roots, and phloem distributes food down from the leaves. A plant can't run from predators or migrate for water. To survive, its cellular tissues have to specialize in extreme physical durability and highly localized resource management. Animal tissues operate under an entirely different set of rules. Animals move. As a result, their tissues form a dynamic, living matrix engineered for complex mobility and internal protection. Epithelial tissue forms a continuous protective barrier covering organs and lining the body's cavities. Beneath that, connective tissues hold the machine together. This includes blood acting as a fluid transport matrix, dense bone providing a calcium-reinforced framework, ligaments binding bone to bone, and tendons anchoring muscle to bone. Actually moving that framework requires muscular tissue. Skeletal muscles pull the bones under our voluntary control. Smooth muscles handle involuntary actions, like digesting food, and cardiac muscles generate the relentless, rhythmic contractions of the heart. This anatomical diagram outlines a single unit of nervous tissue, the neuron. When the brain commands a muscle to move, the signal enters the cell body through branching dendrites, then travels rapidly down the long central axon to trigger the physical response. Whether you are looking at a microscopic amoeba hunting in pond water or a human nervous system firing signals across meters of tissue, the underlying logic holds up. By strictly dividing labor across highly specialized cells and tissues, biology created an architecture capable of sustaining complex life. When we look at a forest or a garden, it is easy to see a random assortment of flora. But biologically, the plant kingdom is a collection of highly specific architectural blueprints, each engineered to solve the mechanical problem of survival in a particular environment. We can categorize these physical chassis types by their structural support. Herbs are short plants, relying on green, tender stems. Shrubs develop hard, woody branches right near their base. Trees, conversely, build massive, thick, central trunks, pushing their branching structures high into the upper canopy. Then there are plants operating with intentionally weak stems. Creepers spread horizontally, using the ground for structural support. Climbers take a different approach, using those same weak stems to actively wrap around external structures and pull themselves upward toward the light. A plant's macroscopic height and its specific stem structure form its first line of adaptation. It dictates exactly how that organism will establish a base and compete for resources within a ecosystem. Once a plant establishes its structural base, it relies on a dedicated vegetative pipeline. The stem acts as a central highway, continuously pulling water and dissolved minerals upwards against gravity. That pipeline ends at the leaf. The physical connection is the petiole, a short stalk that anchors the broad, flat surface of the leaf, the lamina, directly to the stem. Across the lamina, we see distinct structural patterns called venation. Some leaves use a reticulate design, featuring a prominent midrib with a net-like spread of smaller veins. Others, like grasses, use parallel venation, where the internal transport lines run straight alongside one another. Underground, the resource gathering system mirrors this structural diversity. A taproot system relies on one thick main root driving deep into the soil. A fibrous root system abandons the main anchor, instead spreading a dense, shallow cluster of similar-sized roots. These systems are highly predictive. If you look at this diagram, you can see a direct physiological rule. Plants with net-like reticulate veins almost always have deep taproots. Plants with parallel veins almost always rely on fibrous root clusters. By combining a dedicated underground plumbing network with an optimized solar panel array above, stationary organisms secure the continuous flow of energy and water required to stay alive. Beyond immediate survival, plants must secure generational proliferation. The flower is the specific organ engineered for this task. It begins enclosed in small, protective structures called sepals. When it opens, large, brightly colored petals fan outward, specifically to attract pollinators. Inside, we find the male reproductive hardware. The stamen consists of a slender stalk, the filament, which physically elevates the anther, the small capsule where pollen is produced and stored. At the very center sits the female reproductive organ, the pistil. It captures pollen at the top on the stigma, routing it down a long neck called the style,
directly into the swollen base. This base is the ovary, which houses the unfertilized ovules. When a pollen grain successfully lands, it physically drives a pollen tube down into the ovary. It makes direct contact with the ovum, and a zygote is formed. Mace mechanical interactions allow flowering plants to reliably package genetic material into seeds, ensuring that each new generation can establish itself, even in shifting environments. The standard anatomical blueprint is constantly tested by abiotic factors: temperature, water availability, and soil conditions. Over long periods, these non-living pressures force evolutionary structural changes, known as adaptations.
In extreme arid climates, broad leaves would lose too much water to evaporation. Desert plants adapt by reducing leaves entirely to thin spines. The thick, green, waxy stem takes over the job of photosynthesis, while trapping moisture inside its fleshy tissues. Mountain habitats apply pressure through freezing winds and heavy snow. Trees survive by growing in a strict cone shape, with downward-sloping branches and needle-like leaves. This lets heavy snow slide off without snapping the trunk. In aquatic biomes, the structural needs flip entirely. Plants floating on the surface develop long, hollow, lightweight stems. Submerged plants, dealing with constant water currents, grow highly flexible ribbon-like leaves that bend rather than break under the pressure. A plant's physical form is never a random occurrence. It is a direct, calculated response to the specific limits and pressures of its local biome. Beyond physical architecture, plants function as dynamic systems defined by continuous metabolic activity. They ingest energy, execute growth cycles, and perform gas exchange. They also actively process external data. When exposed to a directional light source, the stems and leaves will physically bend toward the incoming photons to maximize their energy intake. Some responses are incredibly rapid. The mimosa plant processes the stimulus of physical contact and instantly triggers a mechanism to fold its leaves inward. Internally, they isolate and store toxic waste products so they don't poison the host tissue. They move nutrients constantly, and through seed germination, they execute a programmed sequence to push new roots into the soil and new shoots into the air. They may be physically anchored to the ground, but plants are highly active processing systems, constantly reacting to internal needs and external stimuli. The defining feature of this entire system is how it acquires energy. Organisms that synthesize their own food from simple substances are autotrophs. In plants, the broad green leaves act as the primary food factories of the biological world. To manufacture food, the leaf must capture atmospheric carbon dioxide. It does this through stomata, tiny pores scattered across the surface, which are actively opened and closed by surrounding guard cells. Looking at this chemical equation, we see the autotrophic engine in action. The plant draws in carbon dioxide and water. Using the green pigment chlorophyll to capture solar energy, it synthesizes these raw materials into complex carbohydrates. As a byproduct, it releases pure oxygen. This unique solar-powered chemical reaction is photosynthesis. It is the foundational mechanism that captures the energy required to support nearly all life on Earth. To understand exactly where these massive chemical reactions occur, we have to plunge down past the visible tissues into the microscopic architecture. Here, the plant is constructed of tiny individual units called cells. Each cell is bound by a thin outer wall called the cell membrane. Inside, a jelly-like cytoplasm surrounds the central command structure, the spherical nucleus. The cell is the ultimate, indivisible biological unit. Every morphological adaptation, every behavioral response, and the entire engine of photosynthesis physically originates right here. However, the standard autotrophic blueprint is not universal. Some plants do not possess chlorophyll. Without it, they cannot synthesize carbohydrates. Instead, they rely on a heterotrophic mode of nutrition, acquiring ready-made food from outside sources. The cuscuta, or amorbel, operates as a parasite. It climbs directly onto a host plant, embedding itself to survive by draining valuable nutrients, actively depriving the host organism in the process. Other plants grow in environments lacking key soil nutrients and must supplement their diet. The pitcher plant modifies its leaves into deep, hollow jugs with a closing lid. Insects are lured inside, trapped in downward-facing hairs, and dissolved by digestive juices.
Fungi utilize saprotrophic nutrition. Instead of hunting live prey or synthesizing light, they extract their required nutrients by breaking down dead and decaying organic matter in their surroundings. Finally, organisms can rely on symbiosis. In a lichen, an alga and a fungus merge. The fungus extracts water and minerals to provide shelter, while the chlorophyll-containing alga prepares and provides food to the fungus. They share the outputs to ensure mutual survival. Evolutionary architecture is endlessly resilient. When primary systems fail, nature consistently engineers a biological workaround. This interconnectedness solves critical ecosystem flaws. As crops grow, they rapidly drain nitrogen from the soil. While nitrogen makes up the majority of our atmosphere, plants cannot absorb it in its gaseous form. It is entirely locked away from them. The solution is a massive symbiotic exchange. Leguminous plants like peas and beans house rhizobium bacteria inside their roots. The plant provides food and shelter. In return, the bacteria pull gaseous atmospheric nitrogen down into the soil, converting it into a soluble form the plant can easily absorb. Understanding a plant requires identifying its precise mode of nutrition. Autotrophs synthesize their own fuel. Parasites steal it from a living host. Saprotrophs extract it from decay, and symbiotic organisms trade resources to survive. Form follows the requirements of survival. From the density of a trunk to the microscopic geometry of a leaf, every plant organ is a specialized component in a highly integrated biological network. Biology functions as a calculated, highly engineered system of survival mechanics. Every living thing runs a complex program designed to beat the environmental odds. At Arvindra's classes, we look past the syllabus to see how these rules actually operate. To run that program, an organism needs an organized structure capable of reacting to stimuli, growing, and reproducing. But life is a constant negotiation with abiotic elements, the non-living variables like jagged rocks, intense heat, and scarce water. Nature's primary strategy for winning that negotiation is adaptation. It is the process of engineering a permanent physical survival jacket tailored for a specific climate. In the extreme heat of the desert, the camel survives because its physical jacket is heavily customized. Long legs elevate its body away from the scorching sand. To retain internal water, it rarely sweats, produces dry dung, and excretes minimal urine. High-altitude mountain regions demand the opposite engineering. Here, the abiotic threats are freezing winds and snow. Yaks grow long, dense hair to insulate their core temperature, while snow leopards develop thick fur that extends over their feet, acting as built-in snow boots for the frozen terrain. Environmental adaptation is nature's first line of defense. It physically shapes an organism's exterior to conquer its abiotic surroundings. If we scale down past the naked eye, the rules of survival get even more intricate. This microscopic ecosystem is dominated by 4 major groups: bacteria, fungi, protozoa, and algae. Then there are viruses, which sit at the edge of life, requiring a host cell just to reproduce. For any of these organisms to survive across generations, they rely on a master blueprint, DNA, stored tightly inside the chromosomes of a cell. The most basic event in all of reproduction is copying that blueprint. Cells use specific biochemical reactions to duplicate their DNA, giving the next generation the exact information it needs to synthesize proteins and build its body. But biochemical copying isn't 100% accurate. Subtle variations occur. If bacteria live in temperate water and global warming raises the temperature, most die. However, a tiny variation might allow them to resist the heat, surviving the shift. The simplest organisms execute this blueprint through fission. An amoeba copies its nucleus and then splits its body into 2 equal halves. Other single-celled organisms, like the malaria parasite, use multiple fission to divide into many daughter cells. At the micro level, survival relies on rapid, slightly varied replication. It is a mathematical strategy to outpace sudden environmental changes. As organisms evolve specialized tissues, simple cell-by-cell division becomes impractical. They require more intricate methods.
The hydra grows a localized bud for rapid cell division, which eventually detaches as a new independent organism. Humans have even intervened in this process of generational survival through cloning, creating an exact genetic replica of an entire organism. In 1996, scientists placed a Finn Dorset sheep's nucleus into the emptied egg of a Scottish blackface ewe. The result was Dolly. Even though born to a blackface surrogate, Dolly was genetically identical to the Finn Dorset, carrying none of her surrogate's types. We interact with microbes as both essential tools and lethal threats. Friendly bacteria convert milk to curd, while yeast powers the baking and alcohol industries. We even source antibiotics like streptomycin from them. Yet this same microscopic world includes pathogens that cause tuberculosis or malaria, often using carriers like mosquitoes to breach our defenses. Generational survival is a constant negotiation. It requires accurately copying DNA while navigating an invisible ecosystem of microscopic allies and parasitic threats. The journey from reproduction to adulthood takes many forms. Dogs and cows give live birth, while frogs lay eggs. A hatched frog starts as an aquatic tadpole, looking drastically different from its final form, before undergoing the massive biological transformation known as metamorphosis. To extract fuel, food travels from the buccal cavity down the esophagus into the stomach. In 1822, William Beaumont observed a stomach gunshot wound, discovering that acidic fluids break down proteins. Finally, the small intestine absorbs nutrients, and the large intestine extracts water before egestion. Complex life requires the specialized, multi-stage internal factory to extract the raw materials required to fuel its survival. Digested food is not yet energy, it requires a chemical spark. Cellular respiration is the process of breaking down that food to release energy. When this happens using oxygen, it is aerobic. When oxygen is absent, it is anaerobic. As this equation shows, anaerobic respiration occurs right inside your own muscles. During heavy exercise, when oxygen is in short supply, your cells break down glucose without it. The byproduct is lactic acid, which accumulates in the tissue and causes muscle cramps. To prevent that oxygen shortage, humans rely on continuous breathing. When you inhale, your ribs move up and out, and the muscular diaphragm moves down, expanding the chest cavity to pull air into the lungs. Exhalation reverses the process, pushing carbon dioxide out. Other animals secure oxygen differently. Cockroaches pull air through side openings called spiracles into tracheal tubes. Earthworms absorb gases through their moist skin, while fish extract dissolved oxygen using heavily vascularized gills. Let's look at the master dashboard of survival. Adaptation handles the elements. DNA copying ensures continuity. Fission and cloning drive population growth. Metamorphosis navigates development. Assimilation harvests fuel. And cellular respiration finally ignites it. The physical curve of a camel's leg, the microscopic duplication of a chromosome, and the cellular ignition of glucose are parts of a single, hyper-optimized strategy. Life is the execution of that blueprint.
Welcome to the ultimate reverse engineering project. Every living organism is built on a chronological master blueprint, a sequence of complex systems that stack together to keep us alive. And it all starts with the physical scaffolding. Look at this complete structural framework. A human baby is actually born with about 305 separate bones. But as we grow into adulthood, many of those fuse together, leaving us with a final structural count of 206. That framework needs flexibility. This diagram isolates the connection between the hip bone and the thigh bone. Notice how the rounded end fits into a hollow cavity. This ball and socket joint allows for massive range of motion in every direction. Contrast that wide freedom of movement with these specialized connections. On the left, the next pivotal joint restricts movement to just turning and nodding. On the right, the hinge joint of the elbow acts like a door, strictly limiting you to a simple back-and-forth swing. Bones can't move themselves, though. They rely on muscles. And there is a strict biological rule governing how they operate. Muscles can only pull. They can never push. Because of this mechanical limitation, they always have to work in coordinated pairs to move a single bone. Ultimately, a beautifully articulated skeleton is still a static cage. To become a living, moving entity, that framework requires an active internal power generation system. The first step to generating power is acquiring raw materials. This sequence shows an amoeba, a single-celled organism, using temporary extensions called pseudopodia to physically engulf a food particle. Plants, or autotrophs, have to do this entirely differently. Instead of hunting, plants manufacture their own fuel. They use chlorophyll to absorb light energy, which actually splits water molecules apart. That reaction reduces carbon dioxide to create carbohydrates, leaving us with this exact chemical equation: 6 molecules of carbon dioxide plus 12 of water, powered by sunlight, yields glucose, oxygen, and water. For complex life, extracting energy from that glucose always starts the same way. Inside the cell's cytoplasm, the 6-carbon glucose is broken down into a smaller 3-carbon molecule called pyruvate. What happens next depends entirely on oxygen. If oxygen is missing, the process goes anaerobic. In yeast, this causes fermentation, producing ethanol. In humans, pushing your muscles hard without enough oxygen forces the pyruvate to convert into lactic acid, causing severe muscle cramps. But when oxygen is plentiful, the pyruvate enters the cell's mitochondria for aerobic respiration. This pathway breaks the molecule down completely, yielding a massive amount of ATP, the primary energy currency for fueling cellular activities. To sustain that high ATP production, the body needs an enormous, continuous supply of oxygen. This schematic focuses on the human lungs, specifically the tiny balloon-like structures called alveoli at the ends of the airway branches. If you spread out the alveolar surface area of a single human, it would cover about 80 square meters. Generating all that cellular energy is impressive, but it's entirely useless if you can't distribute those resources across the body. That distribution relies on the blood. Red blood cells use a specialized pigment called hemoglobin to latch onto and carry oxygen to tissues. Carbon dioxide, which dissolves much easier in water, is transported mostly in its dissolved form, right within the blood plasma. This cross-section of the human heart maps how that fluid is managed. Notice the dividing wall, or septum. The heart is split into distinct atria at the top and ventricles at the bottom, ensuring oxygen-rich blood never mixes with deoxygenated blood returning from the body. Plants handle their logistics differently. While they move water passively through tubes called xylem, transporting actual food through their phloem system requires an active expenditure of ATP energy to push materials exactly where they are needed. All of this constant cellular metabolism creates a massive logistical problem, the continuous buildup of highly toxic nitrogenous waste. To avoid being poisoned from the inside out, humans rely on the kidneys. Every single day, your kidneys filter an astonishing 180 liters of fluid. Yet, because the kidney tubules aggressively reabsorb the useful materials, the final volume of excreted waste is only about 1 to 2 liters. When those kidneys fail, modern medicine steps in with an artificial substitute. This diagram maps the setup for hemodialysis, where a patient's blood is routed out of their body and pumped through a specialized machine to manually extract that nitrogenous waste. The tubes inside this tank act as a selectively permeable membrane. They are bathed in a dialysing fluid with the exact same osmotic pressure as healthy blood, but zero nitrogenous waste. This concentration difference forces the toxins in the blood to diffuse out into the fluid, cleaning the blood without natural reabsorption before returning to the patient. Transporting oxygen and filtering waste are vital mechanics, but on their own, they operate completely blind. They require a centralized command network to dictate exactly when and how fast they should work. For sudden, dangerous stimuli, thinking takes too long. That's why the nervous system developed the reflex arc. It acts as a direct shortcut, routing sensory input straight to the spinal cord to trigger an instant muscle response, saving milliseconds by bypassing the brain completely. While the nervous system handles these split-second electrical signals, the body also requires a slower, more systemic form of control. That falls to the endocrine system, which secretes diverse chemical compounds called hormones to manage long-term growth and development. The bridge between these two systems sits deep inside the skull. This cross-section highlights the midbrain, specifically pointing out the hypothalamus. When the body detects a deficit, like low growth hormone, the hypothalamus releases a chemical factor that commands the adjacent pituitary gland to take action. These interconnected control systems successfully maintain a single organism from birth to death. But to ensure the survival of an entire species across generations, the blueprint needs one final protocol.
Structurally, reproduction is the precise biochemical copying of the original master blueprint. All of those instructions are physically stored within the cell nucleus on thread-like structures called chromosomes, encoded in DNA. The chemical reactions that copy this DNA are never perfect. These subtle, built-in copying errors create variations in the offspring. Over successive generations, those tiny genetic differences become the foundation for all evolutionary adaptation. We started to quantify this inheritance process in the 1800s. This is Gregor Johann Mendel, a scientist who meticulously counted and tracked the inheritance of specific traits across generations of pea plants, establishing the definitive rules for genetic dominance. In humans, that genetic inheritance determines a newborn's sex right at the moment of fertilization. As this diagram illustrates, if the gametes cross to pair an X chromosome with a Y chromosome, the offspring develops as male. If two X chromosomes pair, the offspring develops as female. From the first division of cells to the complex articulation of bones, the ultimate output of all these internal processes is the successful continuation and gradual evolution of life itself. Let's lock this blueprint down. A mature physical framework requires 206 bones, which rely on pulling muscles, which require massive amounts of mitochondrial ATP to function. That ATP production creates metabolic waste, requiring the kidneys to process 180 liters of daily filtrate, keeping the organism alive just long enough to copy its DNA and pass the blueprint on. Here's your critical vocabulary dashboard: synovial fluid, cartilage, ATP, hemodialysis, hypothalamus, and chromosomes.
Memorize how they connect. The internal logic of life reveals itself only when you track these systems as one continuous, interconnected sequence. Master that progression, and you've secured the roadmap to conquering this entire module for your exams.
Every time you eat, you are completing a biological transaction. You are taking raw energy pulled from the earth and transferring it directly into your own cells. A seedling exerts significant physical force, splitting the soil as it rapidly transforms minerals and sunlight into biological mass. To understand how we engineer that mass to feed billions of people, we first have to isolate the microscopic demands of the human body. Human cells run on specific chemical inputs. Carbohydrates and fats provide raw combustible energy, while proteins rebuild physical tissue. Micronutrients, your vitamins and minerals, manage the body's defense systems. We can isolate these nutrients in real time. If you apply a dilute iodine solution to a food sample and it turns deep blue-black, you've just chemically confirmed the presence of starch, a complex carbohydrate. Similarly, exposing a food sample to copper sulfate and caustic soda will trigger a distinct violet color change if the sample contains protein. This 3D anatomical model maps the exact physiological failure points when micronutrients are missing. A lack of vitamin B1 causes beriberi, which weakens the muscles. Missing vitamin C leads to scurvy, causing bleeding gums, while an iodine deficiency results in the swelling of the thyroid gland, known as goiter. If a person experiences a prolonged lack of both energy-giving carbohydrates and tissue-building proteins, physical growth can halt entirely, leading to severe weakness and impaired mobility. Securing these specific chemical inputs is the primary biological objective of a functioning food supply. When staple crops lack enough micronutrients to prevent disease, governments intervene. They inject vitamins and minerals directly into supplies like rice, wheat, and oil, a process known as fortification, marked by the official FSSAI+F logo. But before you can fortify the food, you have to grow it. In India, mass crop production is strictly dictated by two massive climatic windows. The first is the Kharif season. Sown in July and harvested by October, these crops are entirely reliant on the heavy southwest monsoon rains. The second is the Rabi season. These crops are planted in the dry winter months, from October to March, relying heavily on preserved soil moisture and irrigation. Aligning millions of acres of planting schedules with these natural water cycles is the first required step in engineering a stable national food supply. The next step is physical. Before a seed can grow, the hard earth must be tilled. Turning the soil with a heavy plow allows root systems to breathe and promotes the growth of earthworms and beneficial microbes. While traditional hand sowing scatters seeds unevenly, A mechanical seed drill utilizes multiple tubes to pierce the earth, burying seeds at a uniform depth and covering them instantly. Seeds also require chemical support. Organic manure, made from decomposed animal and plant waste, physically improves the soil by adding humus, which dramatically increases how much water the earth can hold. Conversely, factory-made inorganic fertilizers deliver a highly concentrated dose of nitrogen, phosphorus, and potassium. However, applying these synthetic chemicals excessively degrades the soil's pH and pollutes local groundwater. Balancing the organic structure of the soil with precise chemical enhancements allows farmers to sustain high-yield harvests year after year.
But high yields demand consistent water. Historically, farmers relied on manual extraction, like the traditional moat pulley system, lifting groundwater one bucket at a time. Today, large-scale agriculture relies on automated conservation. A sprinkler system mimics natural rainfall, distributing water evenly across highly uneven terrain where flooding isn't possible. In extreme drought conditions, farmers deploy the drip system. By delivering water drop by drop directly to the root base, evaporation is minimized and waste drops to zero. Farmers also manage scarcity spatially through intercropping. By alternating rows of different plant species, they ensure different nutrients are extracted from the soil, while naturally creating a physical barrier that stops pests from wiping out a single crop. Together, these targeted water and spatial management technologies act as humanity's primary defense against geographic limitations and climate stress. Faster, more energetic pace. Once mature, the energy must be extracted. An industrial combine harvester moves through a field, cutting the stalks and immediately threshing the crop to loosen the edible grain from the protective husk. The final physical separation is called winnowing. Using high-velocity wind, the heavier, nutrient-dense grain falls straight down, while the lighter, discarded chaff simply blows away. The extracted grains are immediately moved into massive, highly controlled silos. Here, strict fumigation protocols are executed to keep rodents and aggressive fungal infections away from the food supply. Mastering this final sequence of mechanical extraction and secure storage prevents months of agricultural engineering from degrading into devastating food waste. Animal husbandry acts as a secondary layer of the food system, concentrating raw plant energy into high-density proteins like milk, meat, and eggs. To maximize milk production, cattle farmers utilize specific crossbreeding programs. They combine the long lactation periods of foreign exotic cattle with the rugged, natural disease resistance of local breeds. Commercial poultry facilities run on strict genetic specialization. Birds are specifically bred and fed either to maximize their laying capacity for eggs or to rapidly develop muscle mass as broilers for meat. Out on the ocean, marine fisheries no longer rely on blindly casting nets. Commercial fleets use live satellite imagery and acoustic echo sounders to actively hunt and pinpoint massive schools of fish in deep water. Even insects are optimized. Commercial apiculture heavily relies on the Italian bee because they naturally yield more honey, stay in their hives longer, and sting far less than aggressive local varieties. By engineering these animals and insects, we diversify our protein and caloric sources, establishing a multi-layered security net that farming plants alone cannot guarantee. This dashboard maps the entire sequence. At the micro level, it connects macronutrients directly to cellular diseases. Expanding outward, it links population needs to precise water cycles and soil chemistry. Finally, crops feed a secondary web of livestock, returning dense protein to humanity. Human health does not happen by accident. It is sustained entirely through the relentless. A thunderstorm discharges millions of volts of electricity from the sky, while below, the ground tears apart, destroying infrastructure in seconds. These events look like random chaos, but are entirely predictable under the laws of physics. Both are simply the physical release of massive stored energy. Today, we are breaking down the exact mechanics behind two specific types of energy release: electrostatic discharge in the atmosphere and kinetic tectonic snaps in the Earth's crust. Welcome to today's lesson at Arvindra's classes. Mastering the physics of how this energy accumulates and releases is essential for your geography syllabus, and it is the strict basis for all modern disaster management. To understand a massive atmospheric lightning strike, we have to start at the microscopic level. Around 600 BC, the Greeks noticed something strange. When they rubbed amber with animal fur, it suddenly attracted light objects. They had discovered static electricity. It took over 2,000 years to scale that idea up. In 1752, Benjamin Franklin proved that the tiny sparks jumping off winter clothing and the massive bolts of lightning in the sky were the exact same phenomenon. This animation shows how it works. When certain objects rub together, friction forces the physical transfer of electrons from one surface to the other. The object losing electrons is left with a positive charge. The object gaining those electrons takes on a negative charge. These charged objects now follow a strict rule. Like charges repel each other, and opposite charges attract. As long as they sit there, the electric charges are static. They only become a threat when they find a conductive pathway to move. That sudden, violent motion of charge is an electric current. Since we cannot see electric charge with the naked eye, we need a mechanical way to detect it. This diagram shows a gold leaf electroscope. It consists of a metal rod extending into a glass bottle with 2 strips of aluminum foil hanging from the bottom. Glass is used because it has very low conductivity. When a charged body touches the top wire, the charge travels down and distributes evenly across both foil strips. Because both strips now carry the exact same charge, they violently repel each other and swing apart. If you touch that charged metal with your bare hand, your body acts as a conductor. The charge flows through you and directly into the ground. This process of safely transferring charge into the earth is called earthing. That same tabletop principle is used in civil engineering. Earthing wires are built into high-rise buildings to capture leaking electrical currents and route them harmlessly into the soil, preventing fatal shocks. Now apply those exact same rules of static charge to a volume of air the size of a city. Inside a thunderstorm, heavy water droplets plummet toward the earth while strong air currents rush upward. This massive continuous friction acts just like rubbing the plastic and polythene. This diagram maps the resulting charge segregation. Positive charges pool near the upper edges of the clouds. Negative charges gather heavily at the bottom. Meanwhile, positive charges accumulate on the ground below. Under normal conditions, air is an excellent insulator. But as these massive pools of opposing charges grow, the electrical potential becomes too great. The air's resistance breaks down, and it begins to conduct. The negative and positive charges violently collide to balance the equation. This rapid electric discharge flashes at roughly 27,000 degrees Celsius. That extreme temperature instantly superheats the air, literally ripping apart molecules to create a glowing, temporary hole in the atmosphere known as a channel. A fraction of a second later, the current stops, and the channel violently collapses back in on itself. The acoustic shock wave generated by that collapse is what you hear as thunder. The mechanics are identical to a static shock from a plastic pen. It is just scaled up by millions of volts. Because we cannot stop the physics of a thunderstorm, survival relies entirely on redirecting the energy. This diagram illustrates a lightning conductor. It is a thick metallic rod placed along the highest edge of a building, extending up into the air. The rod provides a highly conductive direct pathway. When lightning strikes, the immense electrical energy ignores the building entirely, traveling straight down the rod and dissipating safely into an underground metal plate.
If you are caught without architectural protection, you have to manage your own conductivity. Stay securely inside. Unplug all appliances. Avoid tall trees and metal poles. Do not lie flat. Instead, crouch down low to minimize your contact area with the ground. The goal is always the same. Give the current a path of least resistance that does not include your body. We see a similarly destructive release of stored energy deep inside the Earth's crust. But here, the energy is kinetic. An earthquake is a short, intense shaking of the Earth's surface caused by the sudden release of mechanical tension. This diagram breaks down the specific terminology of a quake. The exact subterranean point where the disturbance begins and the kinetic energy snaps is called the focus. Directly above that, on the actual surface of the Earth, is the epicenter. The collapsing buildings and fractured roads we see on the news are just the secondary seismic waves rippling outward from that central underground fracture. This global map shows that the Earth's outer layer is not a continuous solid shell. It is highly fragmented into massive slabs of rock called tectonic plates. These plates are in constant motion. When they grind past one another, or when one plate is forced underneath another in a collision, intense friction builds up until the rock finally snaps. The boundary lines where these plates meet are the weakest points in the Earth's crust. We call these vulnerable areas seismic zones or fault zones. This map highlights the pressure points specific to the Indian subcontinent, driven by the upward movement of the Indian plate. The highest threat areas are concentrated along the north, Kashmir, the western and central Himalayas, and the entire northeast region. High seismic risk also extends through the Rann of Kutch, Rajasthan, the Indo-Gangetic Plain, and a few specific pockets in South India. While tectonic shifts account for the vast majority of earthquakes, localized tremors can also be triggered by violent volcanic eruptions, massive meteor impacts, or subterranean nuclear testing. Knowing exactly where these weak zones lie allows civil engineers to anticipate where the crust will eventually break. Because we cannot stop tectonic plates from colliding, we have to measure their output to build appropriate defenses. This diagram illustrates a seismograph, the instrument used to record earthquakes. It relies on the simple principle of inertia. The base is fixed and moves violently with the shaking ground, but the suspended pendulum bob remains perfectly still, allowing a pen to trace the exact differential in motion. That recorded data is then converted into a single magnitude number on the Richter scale, standardizing the measurement of a quake's total power. Any magnitude registering higher than a 7 on the Richter scale is classified as highly destructive. Both the catastrophic Bhuj and Kashmir earthquakes surpassed 7.5. In known fault zones, construction must adapt. Heavy concrete and complex structures are liabilities. Instead, using mud and timber and implementing quake-safe structural blueprints developed by facilities like the Central Building Research Institute drastically reduces casualty rates. Earthquakes strike entirely without warning. Robust building science and strict geographical preparation are our only defense mechanisms against kinetic waves. Let's lock in the core mechanics for your exams. Lightning starts with the same principles of friction discovered by the Greeks and mapped by Franklin. Massive charge segregation inside storm clouds completely breaks down atmospheric resistance, resulting in a 27,000-degree electrical discharge. Earthquakes are kinetic. Tectonic plates grind together, building friction until the rock snaps at an underground focus, sending destructive waves up to the epicenter. Whether it's an electrostatic spark in the sky or a kinetic tremor in the earth, natural phenomena are just the physical balancing of extreme energy. This dashboard compares the mechanisms and measurement tools of both phenomena. Take a screenshot of this now. It contains the high-yield vocabulary you need for your finals. Keep studying the mechanics and stay safe. Thanks for watching Arvindra's classes.
To understand how biological life survives on Earth, you have to start with the baseline physical environment that makes it all possible. Our planet is wrapped in a tenuous, shifting envelope of gases we call the atmosphere. This chart breaks down exactly what you are breathing right now. It is overwhelmingly nitrogen, sitting at 78%. Oxygen makes up roughly 20.9%, followed by argon at 0.9%, and carbon dioxide occupies a tiny sliver at just 0.03%, alongside water vapor and trace gases. But that air doesn't stop at the ground. If you move underground, you'll find earthworms and other soil-dwelling animals constantly digging burrows. Those tiny tunnels create physical spaces that allow the atmosphere to filter into the dirt. The atmosphere is a continuous layer extending from high-altitude clouds down into the subterranean soil, forming the mandatory chemical baseline for every living thing. When you combine that non-living physical environment with living organisms, you get an ecosystem. The botanist A.G. Tansley coined the term in 1935 to describe this structural and functional unit where biology and the environment constantly interact. The defining feature of any ecosystem is the flow of energy. It is strictly one-directional. Autotrophs, like green plants, capture exactly 1% of the sunlight hitting their leaves and convert it into chemical food energy. This energy flow model shows the strict limit on how energy moves. When a consumer eats a plant, 90% is spent on digestion, body heat, and basic work. Only 10% is actually converted into body mass and passed on to the next predator. This diagram shows that 10% rule actively playing out across 3 distinct biomes. The energy strictly moves upward along the arrows, from the producers at the bottom to the tertiary consumers at the top.
Because 90% of the energy is lost at every single step, the math dictates that food chains can rarely exceed 3 or 4 trophic levels. By the 4th level, available energy is virtually exhausted, making top-tier predators highly vulnerable to systemic collapse if the bottom of the chain is disrupted. Forests operate as massive, self-sustaining filtration systems. The tall upper canopy acts like a roof, regulating temperature and light, while the real chemical processing happens silently down on the forest floor. Millions of microscopic decomposers convert those dead plants and animals into humus. This dark organic matter holds intense moisture and releases trapped nutrients right back into the soil, where they are immediately absorbed by the roots of living plants. This data visualization tracks the current scale of these ecosystems in India. According to the 2021 India State of Forest Report, the nation's actual forest cover sits at 21.71%, while the total green cover, which includes scattered tree cover, reaches 24.62%. These layered systems function as massive terrestrial sponges. The complex root structures physically bind the dirt to prevent soil erosion, while allowing rainwater to slowly permeate the earth and maintain the underground water table year-round. Human populations generate massive amounts of organic waste, and to deal with it, we rely on engineering that explicitly replicates that natural decomposition on an industrial scale. This flowchart tracks the physical removal process inside a treatment plant. Wastewater first flows through bar screens to catch large debris, then enters a tank where the flow speed is drastically reduced, causing heavy sand and grit to drop to the bottom. The water then flows into a massive, sloped settling tank. The remaining solid waste sinks to the center and becomes sludge, which is continually removed by mechanical scrapers. What is left is clarified water, which gets pumped full of oxygen. This aeration phase rapidly breeds aerobic bacteria, microbes that require oxygen to survive. They multiply and aggressively consume any remaining organic waste. Modern sewage treatment is essentially accelerated biology. By combining physical screens with billions of hungry microbes, we process hazardous waste into safe, clean discharge and nutrient-rich agricultural manure. When that engineering fails or simply doesn't exist, the biological consequences are immediate. Untreated human waste pollutes surface water and groundwater, becoming the primary vector for lethal diseases like cholera, typhoid, and dysentery. To counter this, the Indian government launched the Swachh Bharat mission in 2014. The Phase 1 goal was direct and vital: eliminate open defecation by building millions of localized toilets and achieving an open defecation-free India. Phase 2, running through 2025, shifts the policy focus to comprehensive solid waste management. It mandates the strict separation of waste, ensuring natural biodegradable organics are isolated from inert, non-biodegradable plastics and metals. You can build the most advanced wastewater infrastructure in the world, but physical engineering requires a massive behavioral shift. National health depends entirely on communities translating these biological realities into daily civic habits. If you scale up from the local water table to the stratosphere, you hit the ozone layer. Ozone, a molecule made of 3 oxygen atoms, is a deadly poison at ground level. But high in the atmosphere, it functions as a crucial shield, absorbing dangerous solar ultraviolet radiation. By the 1980s, that shield was deteriorating. Synthetic chemicals like chlorofluorocarbons, used in refrigeration, were rising and chemically fracturing the ozone molecules. The policy response had to be global. In 1987, the Montreal Protocol successfully forced nations to freeze CFC production. More recently, India ratified the Kissa-goi Amendment, committing to phase down an alternative set of potent chemicals known as hydrofluorocarbons. A local forest requires a balanced food web to survive, and the entire planet requires legally binding, coordinated global treaties to manage the chemicals we engineer. Let's lock in the core terminology. Saprophytes, organisms that feed entirely on dead or rotting matter. Anaerobic bacteria, microbes that survive completely without oxygen. Vermicomposting, using earthworms to rapidly break down biodegradable waste. Bioaccumulation is the process where chemical toxins build up inside a single organism. Biological magnification is when those same toxins multiply in concentration as they travel higher up the food chain. Thanks for watching Arvindra's classes. Pinning down these exact definitions and understanding how a microscopic bacteria connects to a massive global policy is exactly how you master environmental ecology for your exams. Humans have used biology to our advantage for thousands of years. Turning milk into curd or baking a loaf of bread are technically biotechnological processes. But today, the field has moved from the kitchen to the laboratory, where we now directly edit the genetic code of human embryos. The European Federation of Biotechnology defines this modern era as the integration of natural sciences with organisms, cells, and molecular analogs. This represents a shift toward the active engineering of biological systems at the molecular level. Mastering this transition from macrobiology to molecular engineering is a high-yield requirement for the UPSC syllabus. These concepts bridge basic science with global policy, agriculture, and ethics. Modern biotechnology rests on two major pillars. The first is genetic engineering. This is the physical alteration of genetic chemistry, isolating pieces of DNA or RNA to insert them into host organisms and change their observable traits. The second pillar is bioprocess engineering. Once a single genetically modified cell exists, it must be cultivated in massive, strictly sterilized environments. This ensures only the desired microbe grows, free from outside contamination. Genetic engineering provides the biological blueprint, while bioprocess engineering scales that blueprint into millions of doses of antibiotics, vaccines, or enzymes. The modern field traces back to a specific experiment in 1972. Stanley Cohen and Herbert Boyer successfully isolated an antibiotic resistance gene and linked it with a native plasmid of Salmonella typhimurium, creating the world's first recombinant DNA. This diagram of the process shows exactly how they did it. They used restriction endonucleases, often called molecular scissors. These enzymes function by inspecting the length of a DNA sequence, finding a specific recognition site, and cutting the sugar phosphate backbone. The enzymes target palindrome sites, sequences that read the same backward and forward on opposite strands. By cutting slightly away from the center, they leave behind single-stranded overhangs known as sticky ends. Because these ends naturally form hydrogen bonds with their complementary matches, a second enzyme called DNA ligase acts as a biological glue, joining the two foreign strands together. Discovering these natural cut-and-paste tools in bacteria was the primary technical hurdle. With the scissors and the glue identified, the genetic code became an editable medium. This diagram illustrates the delivery system. A loose piece of DNA cannot survive on its own inside a host. It requires a vector, typically a circular bacterial plasmid or a bacteriophage, to ferry the alien code into the cell. For the vector to multiply, it must contain a sequence called the origin of replication, or ORI. This is the specific starting point that allows the host cell to duplicate the new genetic material along with its own DNA. Scientists verify these genetic cuts using gel electrophoresis. Since DNA fragments are negatively charged, they can be forced to move toward a positive anode through an agarose gel matrix. The gel provides a sieving effect. The smallest fragments move the farthest and fastest, separating the DNA into distinct bands so the specific gene of interest can be isolated and purified. Vectors provide the transport, and electrophoresis provides the visual verification. These tools allow scientists to track their work with precision. Isolating a single gene is often just the beginning. Industrial applications require billions of copies. This is achieved via the polymerase chain reaction, or PCR. By heating the DNA, the denaturation step, the double strands separate. PCR uses Taq polymerase, an enzyme from the bacterium Thermus aquaticus that survives extreme heat. This enzyme builds new strands using provided nucleotides, allowing a single DNA segment to be amplified 1 billion times in a few dozen cycles. Once the DNA is amplified and packaged in a vector, it must enter a host cell. However, cell membranes are hydrophobic and naturally resist the passage of hydrophilic DNA molecules. To bypass this, cells must be made competent. Biologists treat the cells with calcium and apply a 42 degrees Celsius heat shock to open pores in the cell wall, or use ballistic gene guns to fire DNA-coated gold particles directly into the tissue. When the host cell finally absorbs the vector, the biological transformation is complete. The organism is now programmed to act as a living factory.
To scale up from laboratory tubes to commercial supply, we use industrial bioreactors. These massive vats, like the stirred tank reactor shown here, process up to 1,000 liters of culture simultaneously. Impellers and sparging systems maintain optimal growth conditions. By pumping in sterile air bubbles to maximize oxygen transfer, these reactors keep cells in their most productive exponential growth phase. After biosynthesis, the product enters downstream processing. This involves separation and purification of the desired protein, followed by clinical formulation and quality control testing to ensure the final drug is safe for the market. Bioreactors provide the volume, and downstream processing ensures the purity. Together, they turn cellular blueprints into viable commercial products. In agriculture, this technology produced Bt cotton. By inserting a specific toxin gene from the bacterium Bacillus thuringiensis, the plant itself becomes lethal to certain pests, reducing the reliance on external chemical insecticides. Medical breakthroughs are equally significant. In 1983, Eli Lilly used these techniques to produce human insulin in E. coli bacteria. Beyond pharmaceuticals, gene therapy now offers a way to correct genetic defects by delivering functional genes directly into a patient's cells. Diagnostics have also advanced. ELISA, the enzyme-linked immunosorbent assay, uses antigen-antibody interactions for early disease detection. It is a core tool for identifying infections like HIV or COVID-19 before traditional methods can. These applications show biotechnology is actively reshaping global food security, human longevity, and infectious disease management. Manipulating life raises serious ethical concerns. These include biopiracy, the unauthorized use of bioresources without compensation, and the potential for corporate monopolies over genetically modified seeds. Regulatory oversight is mandatory to manage these risks. In India, the Genetic Engineering Approval Committee, or GEAC, evaluates the safety and validity of GM research and its introduction into the public sphere. The entire process forms a logical chain: restriction enzymes cut and ligases paste, then vectors deliver, PCR rapidly amplifies, massive bioreactors scale, and downstream processes purify the result. This glossary directly maps out the core scientific terms of the entire biotechnology blueprint that we have covered in this session. Mastering these definitions provides the critical technical foundation needed to understand how we now manage human health and global resources.